Hello and welcome to my explanation video for MunPy, my mission to completely automate a trip to the moon and back in Kerbal Space Program. Before we begin, a few details about how this works. It starts with the Kerbal Remote Procedure Call mod for Kerbal Space Program, which I have linked in the video description. This mod allows the game to take commands through a built-in server, which in turn can receive commands from a number of possible clients. In my case, I ran the game and server on my laptop, while my Raspberry Pi issued client commands through Python over a wired network. I did this to more closely simulate the type of computer that might be controlling a spacecraft, though even then the Pi is fairly powerful. Now, on to the code. As you can see here, I've divided the script into a number of functions. While I only reused a few functions within this script, I did this so that many of the parts could be used for future scripts. We'll start by looking at the Kerbal launch function. This function starts by establishing the active vessel as well as some telemetry information. This information helps the program to decide how the spacecraft should orient itself to reach the target orbit from the launch pad. In this case, I chose to use a fixed gravity turn.
This turn may not work well for all spacecraft, but for my particular launch vehicle and spacecraft, I was able to get a fairly consistent and efficient launch. The turn works by looking at the current altitude of the rocket and calculating a pitch target for that altitude based on a predetermined function. It also checks to see if any engines have burned out, and if so, stages the rocket to either drop empty boosters or start the next sequential stage.
Once the apoapsis, or highest point of the trajectory, meets the target value passed into the function, the throttle is cut and the spacecraft coasts until it leaves the influence of the atmosphere of Kerbal. This allows the program to make its next set of calculations accurately. Our next function, apoCirc, allows the program to calculate the needed burn to circularize at apoapsis. The function looks at how fast the spacecraft will be going at apoapsis in its current trajectory, and how fast it would need to be going in order to be in a circular orbit at that height. Then, using the difference in speed, it can calculate a burn in order to circularize. To make the speed calculations, I used a simple function that implements the vis-viva equation. I also have a similar function for circularizing at periapsis, or the lowest point in the orbit, which will be used when arriving at the moon. The next function, doNode, is the bread and butter of the mission. Given a maneuver node, it performs the corresponding engine burn. It does this by using Tsiolkovsky's rocket equation to calculate the needed burn time. Once it is time to do the burn, it starts the engine and then waits. Once the burn is just about to end, it throttles down and looks at the remaining thrust requested in the maneuver node. Once that reaches 0, the engines are cut, finishing the burn. The program then stabilizes the spacecraft to ensure it's ready for the next part of the mission. With the circularization burn complete, we're officially in space. Now on to planning and executing the burns we need to reach the moon. Moon Transfer handles the whole of the transfer to the moon, from transfer injection to circularization at the target. After establishing telemetry, the function hands things off to the HOMON Departure Planner function. The first part of planning our transfer is to know when to do it. Let's look at the HOMON Timing function. This function starts by pulling in the 6 Keplerian elements. This is a set of elements that fully describe the orbit of a body in a two-body system. Kerbal Space Program models orbital mechanics as several two-body systems, so by using the Keplerian elements, we can understand our trajectory completely. Once that information has been collected for both our spacecraft and our target body, we can calculate another parameter called the mean motion. As the bodies orbit, if their orbit's not perfectly circular, it will change in speed as they change in altitude. Mean motion is the average angular rate of a body throughout its orbit and can be used to make useful calculations. Once we have this value, as well as the angular positions of the spacecraft and the target body in the same reference frame, we can begin to iterate. During our iterations, we make a guess on how long we would have to wait to start a HOMON transfer that would hit our target. Based on this guess, we examine the time of flight for a HOMON transfer starting at that time, and use that to see if we would hit our target. Based on how much we miss, we adjust our guess to try to get closer, ensuring that our adjustment still references a time in the future rather than one in the past. Once our guesses stop changing so much, we're likely to have found the right time to burn, more or less. Once we know when we need to burn, we need to know how much and in what direction we need to burn. To do this, we reuse our vis-viva function from earlier to find the difference in velocity between our current and desired trajectories. As an added precaution, we also make an attempt to correct for orbital eccentricity in our current orbit. To do this, we look at the flight path angle at the time when we burn, or the angle between the trajectory of the spacecraft and the horizon. By looking at this angle, we can make sure that our final trajectory has a flight path angle of 0 as needed for our HOMON transfer. Once we know this final correction factor, we can create and execute our maneuver node. There's one small problem here you may notice. We really are hitting our target. The current course is going to slam right into the moon. This is a difficult problem to exactly calculate a solution to, so I found a bit of a simpler way. I created a function I call HOMON Corrector that attempts to imitate the fancy differential correctors found in commercial software for planning spaceflights. As you can see, my version is a bit simpler than those fancy commercial programs. It takes in a guess and applies it to a maneuver node. Then it changes the maneuver node slightly along the directions the user chooses to modify and sees which of those corrections gets the given target parameter closest to the given target value. Then it changes the burn to include that small addition and starts over again. If no modification gets the target closer, or if it has been iterating for quite some time, it will try a smaller step size to avoid getting trapped by any nonlinearities. This isn't the most robust way to do this, but with a good initial guess, it is able to create some fairly good correction burns. Now that we have a node to correct the transfer, we execute that maneuver. Then we warp into the sphere of influence of the moon and plan and execute a circularization burn at periapsis. From here we enter several smaller functions that together handle the landing process. The first prepares a maneuver to help us land. We start with landing burn prep. The first thing that this function does is find out when the spacecraft will be on the night side of the moon. I did this so that the landing would occur on the day side, which is much more visually interesting. Daylight opposite time is used for this step. To find out when the spacecraft would be on the night side, I looked at the angle formed by Kerbal, the moon, and the spacecraft at the current moment and 100 seconds into the future. Based on whether the angle now or in the future would be closer to my target angle, I could tell if the angle was currently increasing or decreasing. With that in mind, I was able to calculate how long I would need to wait until the spacecraft would be in the right position. This function is an approximation in several ways. It assumes a circular orbit and it neglects the motion of the moon relative to Kerbal. However, since my orbit at this point is close to circular and has a pretty short period, it works well enough. Once we have the timing down, the rest of the function uses a simple application of the vis-viva equation as used in our circularization functions, but this time to lower the orbit to a target value. In this case, the lowest we think we can safely go without hitting a mountain. Once we've executed our prepared nodes, we move on to the constant altitude and suicide burns that conduct the bulk of the landing. The process of a constant altitude burn is fairly simple. The goal is to burn to reduce the spacecraft's horizontal velocity enough to land safely without beginning to descend. This requires the spacecraft to point the engine slightly down to counteract the gravity of the planet or moon. The benefit is that this landing method can be safe if done properly, and there is some ability to choose a landing site by directing more or less thrust upward to control how far the spacecraft travels downrange. After setting up an appropriate reference frame, the spacecraft points retrograde, or against its velocity. Once the spacecraft reaches periapsis, it starts to burn. This control loop uses a simple integral control scheme to angle the spacecraft up and compensate for gravity throughout the burn. Once the horizontal speed of the spacecraft is manageable, we move on to the suicide burn. The suicide burn gets its name because it feels dangerous, and it can be if miscalculated. After reducing horizontal velocity, the spacecraft begins to fall to the surface. To save fuel, you want to wait till the last possible second to begin burning, but if you're too late, you'll crash. The suicide burn function compares an estimate of time to impact against an estimate of how long it will take the spacecraft to come to a stop at the bottom. The estimate of the needed burn is derived from the potential and kinetic energy of the spacecraft, while the impact time is solved for quadratically, assuming a uniform gravity field. This process isn't perfect, so through trial and error I found that 65% of my burn time estimate resulted in a safe but efficient landing. Once it is time to burn, the engines activate at full throttle, but begin to throttle down in order to bring the lander to a safe speed once it hits the surface. And now we have landed! This is exciting, but we still have the return journey to make, so we'll take off again soon. To handle the launch, we have a different launch function than we did for launching off of Kerbin because it needs to make a few different assumptions. One is that stages for the craft are exclusively sequential. It works for the lander I have here, but this is something I would have to change if I were to make use of a different design. The second key assumption here is how the gravity turn works. The loop determining the pitch of the spacecraft assumes here that the spacecraft can almost always be pointed at or nearly at the horizon. This is achieved by having a small delay before pitching over, and the other key part of the loop. The loop checks the surface altitude of the spacecraft, and pitches up in the event that the altitude is getting smaller. This helps keep the spacecraft from running into a mountain. Once the target apoapsis is reached, the same routine as before is used for circularization as apoapsis. Last, we have the moon return function, which handles the burns to set up an aerobrake return as well as splashdown. This is yet another function composed of smaller pieces, so let's take a look at the return burn function first. The return burn function's most important calculation is that of excess velocity. The function looks at the desired target periapsis around Kerbin and determines the velocity an orbit would have if the apoapsis were at the orbit of the moon. This value is compared to the orbital velocity of the moon around Kerbal. By looking at the sign and magnitude of this value, we can tell how fast we want to be going when we escape and whether we want to escape along the orbital velocity vector of the moon or against it, to either raise or lower the axis opposite the spacecraft when it escapes. Then, we can use some math for hyperbolic trajectories, as well as a technique similar to what I used in the process for waiting until the light side to figure out how fast we need to go at periapsis to get our desired trajectory, as well as when we should burn. This function makes two key assumptions: that the orbit is counterclockwise and that our desired excess velocity is negative relative to the moon's orbital velocity. The latter need not be an assumption, however, since I knew it would always be the case for this mission, I omitted the other case in my code. Unfortunately, since all the vectors and objects we have referenced up to this point are moving, our burn as planned is not quite perfect, so the program also runs around at the corrector program I discussed earlier. After executing the maneuver planned previously, the spacecraft warps out of the sphere of influence of the moon. Then, it conducts another correction burn to make sure the spacecraft enters the atmosphere at the correct altitude. The burn is in the normal direction to the orbit, changing the inclination. This is done because this type of burn has a small amount of influence on the altitude of reentry, so the burn is large enough to be conducted accurately. Lastly, for entry, descent, and landing, the program hands off to the landing handler function. This function is fairly simple. It warps near to periapsis and waits until entering the atmosphere. Then, it checks to see if it is safe to release the parachutes, and when safe, releases them. If, before the speed is low enough to release the parachutes, the spacecraft leaves the atmosphere, there is a contingency to warp again so as to reduce time spent waiting. And splashdown! Thank you for following along with the MunPy mission. I would like to thank the creators of Kerbal Space Program for developing this amazing game/orbit mechanics simulator, and the creator of the remote procedure called mod. I won't try to pronounce your name, but it's up on the screen now. Thanks for watching!